Hi everybody. The next section we want to look at is 4.8 on antiderivatives, and this will be the last section of chapter 4. So we're kind of, like I said, working our way toward, we're pretty much done with the first part of calculus, like I said, which is differential calculus. And so what we want to start looking at in this section is the second part I was mentioning, which is integral calculus. And again, that has to do with calculating areas. You probably won't see the connection in this section, but we'll get to that pretty soon in chapter 5. But the idea behind this section is sort of, normally if you're given some function, I would ask you to find its derivative, right? But now we're going to go backwards the other way, right? I'll give you some function, the derivative of some function. I'll ask you, okay, well, what function did I take to get the derivative of that? And that can be a little bit trickier, but we actually did that a little bit already in one of the previous sections. So let's define this. So a function capital F is an antiderivative of some function little f if the derivative of the function capital F is equal to f of x, right? So basically exactly what I just said, right? If you're given some derivative of some function, right, you want to find, well, what was the function that I took the derivative of to get that, right? Normally we would go this way. Now I'm asking you to go in reverse, right? That's why it's called an antiderivative. One thing I want to warn you about, and I think I mentioned this before, is for antiderivatives, don't forget that you can always have an arbitrary constant, right? Because if you take the derivative of some constant, you'll get 0. And that kind of makes sense, right? I mean, if you have a bunch of curves that all have the same slope, but they're just shifted up or down by some constant, they will all have the same slope no matter where they are, right? So, so if you're looking for the antiderivative of something, you have to add an arbitrary constant on there. And here's a list of some antiderivatives. Some of these you'll sort of know already. So this is if you have some power function like, say, x to the 5th power, then the antiderivative of that will be x to the 6th, right? You have to add 1 to the power, which makes sense, right? Because when you take derivative, you bring powers down. And then you have to divide by that number, right? So if you have like I said, if you have x to the 5th, its antiderivative then would be x to the 6th over 6, right? Because, plus I should say plus some constant, right? Because if you can always check your answer by taking the derivative and see if you get this back, right? Because if you take the derivative of this, you get that, and again, you have to add that constant because the derivative of a constant is 0, right? Antiderivative of this is that. So remember the derivative of cosine is negative sine, so the antiderivative of that would be that, where k is just some number. So if you have like sine of 3x, that would be 1 over negative 3 times cosine of 3x plus c. We'll have a similar thing for cosine, secant, cosecant. Some of these are obvious, but some of them are a little bit harder to figure out. Like, so for example, the antiderivative of e raised to some number times x. So if, let's say you got e to the 5x, that'll be 1 over 5 times e to the 5x. Or if you have e to the negative x, that would be 1 over negative 1 times e to the x, right, plus some constant. The antiderivative of 1 over x is the natural log of x, because remember the derivative of the natural log of x is 1 over x. Antiderivative of this is that. Antiderivative of that is that. Antiderivative of that is that. And so you can think about these. They all make sense if you want. But you can also just think of this as something that you have to memorize or put on your formula sheet, and then just make sure you do the homework so you can practice with them and see what they mean. But if you think about it, these all do make sense, right? And you can always check these. Like I said, if you're not sure if these are right, take the derivative of this side and you should get that back, right? So if you want to check and see, is this the right antiderivative of that, take the derivative of this and you should get sine of kx, right? And that should be true for all the things here. A couple things about antiderivatives is if you take the constant times a function, its antiderivative will be a constant times that function. So if you've got, like, say, for number 1, for example, like let's say you've got 7x cubed, right? Just pull the 7 out and then take the antiderivative of x cubed, which would just be x to the 4th over 4, right? Because remember, when you're taking the antiderivative, you add 1 to the power and then divide by the same thing. So that would just be 7/4 times x to the 4th, right? Same thing with a negative, right? If there's a negative in front, you can just pull that out and then take the antiderivative. And then you can also add or subtract antiderivatives, right? So if you've got, say for example, like let's say you've got x squared plus x cubed minus x to the fifth, right? That would just be x cubed over 3 plus x to the fourth over 4 minus x to the 6 over 6. Right? You can just do those separately as long as you're adding and subtracting. Now, if you're multiplying and dividing, that's a different story. We'll get to that eventually. So the collection of all antiderivatives of f then is called an indefinite integral, and I may refer to that as the antiderivative, and is given by this symbol. So this is sort of an elongated s, and this notation is sort of similar to the notation for summation, in the sense that this is the Greek letter s, sigma, but you sort of think of this as a more continuous thing, where this is more discrete. Right here, the index is going up, typically in increments of 1 to whatever number, right? So you go from 1 to 2 to 3. But think of this as a more continuous thing, where maybe you're going from 1 to 3, but you're including all the numbers in between, not just the integers, right? So maybe like 1 and then 1.001 and then 1.002, etc. Right? I mean, I can't list them all, there's infinitely many. But this symbol is called the integral sign, and the function here, the thing inside the integral, is called the integrand. That's the thing you're integrating. And this dx here, we'll talk about that later, but that's basically just indicates what variable you're integrating with respect to, in case your function has more than one variable or something like that. So just kind of get used to this notation. This basically just means the same thing as the antiderivative, right? So if I give you some function and I ask you to find its antiderivative, I might write it this way. Or if I ask you to find the integral, or maybe the area, right, you could write it that way. We'll talk more about that in the next chapter. But so let's just use this notation then to find some antiderivatives. So again, basically all this notation means is that I want you to find the antiderivative of the function here sandwiched between this weird elongated s symbol and the dx there, right? So again, for x here, remember you have to add 1 to the power. So the 4 to the x, right, that would become 4x squared over 2. Remember, these two have to match. And then 2 goes into 4 twice, so you get that. For the second thing here, right, you can pull out the 2, and then think of that as x to the minus 1/2, right? What would you do for that? Well, and be careful, don't accidentally take the derivative. Don't bring the negative 1/2 down in front. Remember, you want to add 1 to the power. So the antiderivative for that then would be 2x to the positive 1/2 divided by 1/2, which would give you 4 times the square root of x, right? Plus some constant, right? So the antiderivative of this will become that, right? Now for something like this where you're dividing, don't forget that you can break this up into 2 separate fractions and then reduce the fraction, right? So x divided by x to the 5/4 is the same thing as x to the 1 over x to the 1/4, and this will become 2 over x to the 1/2. So again, you want to think of this, if you prefer, as x to the negative 1/4. So add 1 to that power will give you x to the 3/4 divided by 3/4, or if you're dividing by 3/4, that's the same thing as multiplying by 4/3. And then this you can write as 2x to the minus 1/2, right? So add 1 to that power, you'll get 2 times x to the 1/2 divided by 1/2, right? And so that will give you, I guess it's basically the same thing we did up here, right? That will give you 2 times 1 over 1/2, which will be 4 times x to the 1/2 plus c, right? This one, again, since you're adding or subtracting, you can just break up each integral separately. Sorry, I guess I should have a dx here after each one of these. I guess I kind of forgot that one. So what's the antiderivative of this, right? You can just pull the 3 out. Antiderivative of cosine. Again, if you forget, you can look back at that table, but if you think about it, hopefully that'll make sense. Antiderivative of cosine is just sine, right? Because in that case, k is just 1. Cosine of 1x is equal to 1 over 1 times sine times 1 of x. And the antiderivative of negative sine 3x will be negative sine of 3x divided by 1/3, right? Which will give you positive 1/3 cosine 3x. And then you might wonder, well, don't you get a separate constant for each one of these? Well, yeah, I guess you do, but it's still just a constant, so you could just add those together into one big constant. And if you prefer to call these two different things, so that there's two different constants you can, but you know, you're just going to glom them together into one big constant anyway. Let me maybe zoom in here so you guys can see this a little bit better. So like if you look at this one, what would this be the antiderivative of? Well, for here, first of all, you can pull the constant out, and then, like I said, if you forget, you can always look at the table. So look at cosecant x, cotangent x. That would be, I guess, this one down here, where k would be 1. Right, so that would just be 1 over -1 times cosecant of 1x. Well, that's just going to be cosecant x, and then I guess you'll have the negative for that, and then you'll just have, again, don't forget to add your constant on there. Right? For something like this is an x here, so they got kind of cut off there. For this one, again, you can pull the 2 out front, and then this one is a little bit tricky. We'll talk about this one a little bit later more maybe, but this one you kind of just have to recognize the fact that the derivative of this would be that. We'll talk about some methods for integrating these later. That one is kind of tricky though. For this one, again, you could just pull the 2 out front, break up the integral into 2 separate integrals here. And then what's the antiderivative of e to the x? Well, again, that's a little bit trickier again. You know, I suppose if you wanted to, you could think of this as, you know, e to the x to the 1/2. You know, there you're raising a power to a power, so that would just be e to the x over 2. And then you can employ this rule where, I guess, k would be 1/2, right? So that would be, the derivative of that then would be 1 over 1/2 e to the 1/2 times x, right? And that'll just give you 2, so that's where that 2 is coming from. And then again, don't forget your constant. And then I guess this one I should have moved down a little bit more, so I should put a space in there. What's the antiderivative of tangent x? Again, one thing I should mention is, you know, not all the integrals are on this table. If you look in the back of your book or go online, you should be able to find a table of integrals somewhere. If you want to use that. So some of them you may have to look up in the table. We'll actually talk about how to derive some of these from scratch later on. And then here's this integral, right? You've got e to the 2x over e to the 2x plus 4. Again, you might have to look that one up in a table also. But that will turn out to be this. And then again, don't forget your arbitrary constant there. So we'll look up, you know, most of these I'll expect you to do from scratch on the exam. And like I said, I'll show you how to do these eventually using some more advanced techniques. But, you know, a lot of these integrals have been worked out over the centuries. Remember, calculus is, I guess, probably well over 200 years old by now. It's not like mathematicians have been sitting around doing nothing. So if you do want to, you know, if you want to look at, like, if you bought a copy of the book, that should be fine. Otherwise, you can go online and find a table of integrals somewhere. Okay, that brings us to something a little bit more complicated, and that is initial value problems. You might wonder, well, why do I have to keep adding this constant on here? Well, one reason is because, you know, if you take the derivative of this, you know, it will give you that back. So in a way, antiderivatives are not unique, right? When you're taking the antiderivative of something, you get a whole bunch of curves that are just shifted, you know, the same shape, but just shifted up or down from one another. Initial value problems sort of allow you to single out a single curve. They'll give you sort of initial conditions that you want the curve to satisfy, and then that will let you pick one of those infinitely many curves. It will basically allow you to figure out what that constant is. So let's say I want to find the function satisfying this equation. This kind of gets into differential equations a little bit, which we'll talk about later. But I'm trying to find the function so that if I take its derivative, I get this, right? Well, what function is that? Well, that would just be 4 sine of x, and then, again, don't forget your constant. And then how do I figure out what c is, or how do I pick out one curve from this infinitely many values of c? Well, I use my initial conditions. I want to pick the curve so that when x is 0, the curve goes through 3, right? When x is 0, y is 3. So I'll just put 0 in for x. Well, sine of 0 is just 0. That disappears. And then f of 0, my y-coordinate, that's just 3. So this constant, whatever it is, for these initial conditions must be 3. And so that would give you the particular solution that you're looking for, right? So the initial value problems are used a lot in like differential equations in physics, right? This might mean like you have like maybe you have something oscillating back and forth like a spring, and you know that at time 0 the original oscillation of the spring is at height 3 or something. You can use that to find the equation of the oscillating spring. Here's another example. Now this one's even a little bit more complicated because here we've got the second derivative, and I give you sort of initial conditions for the derivative and the original curve. So again, this says I'm taking the second derivative of some curve, I'm getting 0. What would that curve be that satisfies these initial conditions? So take the antiderivative of this, right? We'll think about, well, what would I take the derivative of to get 0? Well, that would just be some constant. And then what would I take the derivative of to get the constant? Well, that would just be, and I can use my initial conditions here to find the value of c, right? I know when the first derivative is 0, c is 2, so that implies that c is just 2. So what's the antiderivative of 2? Well, that would be 2x plus some other constant, and again, I could call it c again, but that might confuse me with my original constant, so I'm just going to call it d, or you could call it c with subscript 2 or something. And then use those initial conditions, right? So this says that when x is 0, y is 0. So if x is 0 and y is 0, that implies that d is 0. So the function that I can take the second derivative and get 0 that satisfies these initial conditions is that. Right? And this is an example of a differential equation, right? When you're solving a differential equation, you're trying to find a function that makes the equation true, right? Not just a number. Let's look at an even more applied example. So like I said, one thing you can use this for is motion. So let's say that we want to find the position function if we know that the velocity function of some particle is this, and we know at time 0 the position is, say, 1, who knows what this is measured in, 1 meter, right? So this is my velocity, so if I want to find the position, take the antiderivative of that, right? What would the antiderivative of that be? Remember, the antiderivative of e to the kt is 1 over k times 1 over k, or times kt, right? So in this case, k would be -1, so that's just going to be -1 times e to the negative t. I can multiply that by that constant. Here I have to add a t, and then don't forget I have to add an arbitrary constant onto the function, right? Because it's the antiderivative. And then I want to try to find the specific function, position function, so that time 0, the initial position of the particle or whatever is moving is 1 meter or whatever, right? 1 meter, 1 foot, whatever this is measured in. So when I plug 0 in for t, right, I'll get -3 times e to the 0, so that'll be, so in other words, s of 0, that'll just be -3e to the 0 minus 2 times 0 plus c. Well, I know that this is 1, right? S sub 0 is 1, and e to the 0, that's just 1 either. So I get -3, this will be 0 plus c. So if I solve that for c, I'll just get c is equal to 4. Right? So then just plug that back into your equation, and that gives you the specific position function that satisfies your initial condition. So that, don't forget that constant when you're doing the anti-differentiation, because that's important, right? You know, like for example, if you didn't do the constant on this one, you wouldn't get the right answer for this, right? So when you're taking the antiderivative, don't forget that you always have to add that arbitrary constant, unless you have numbers on the limits. If you have a definite integral, and we'll talk about that more later on, you might wonder, why would you want to put numbers on there? Well, like I said, it turns out that what we're really sort of calculating here is an area. We'll talk about that later. So for right now, when you're doing an indefinite integral, if it doesn't have numbers, if you're just finding the antiderivative, don't forget to put that constant on there. Okay, well, that wraps up Chapter 4, and like I said, the first part of the course. So in Chapter 5, we'll move on to the second part, which deals with integration or finding areas. And it turns out that integration has to do with finding the antiderivative, which is sort of the big deal with calculus, and we'll talk about how that works.